Some of the heat from a hot object, like this iron ball, is transferred to the surroundings by radiation. Radiation differs from conduction and convection in that no material medium is involved. Radiated heat will travel through a vacuum. The radiation cannot be seen, but can be felt. And this detector measures the radiation. Radiated heat can also be detected photographically, using film sensitive to infrared rays. These rays are one example of a form of energy transmission called electromagnetic radiation. This was taken in darkness. The infrared radiation from the hot ball affected the film, producing this picture itself. The other examples are light rays, radio waves, X-rays, and the ultraviolet rays that produce your suntan. The only way in which these various electromagnetic rays differ from each other is in their wavelength, and this difference accounts for their very different properties. The white light produced by the sun or other very hot bodies is a mixture of rays of different wavelength. This can be shown by passing white light through a prism. The different wavelengths are separated, producing the familiar rainbow colors of the spectrum. Rays of short wavelength produce violet and blue colors. Longer rays produce the yellows, and longer rays still, the red. Infrared rays have a wavelength longer than the visible red rays. Their presence can be shown with this detector. As it is passed across the visible spectrum, there is a small reading on the galvanometer. But when the detector passes beyond the red end of the spectrum, the current increases even more, showing that there is much radiation at that point, the infrared. Warm bodies, like the iron ball, give off infrared rays invisible to the eye. But hot bodies, like the sun, produce both infrared and visible radiation. Light and infrared rays have many features in common. Both can be reflected and focused using appropriate mirrors. This is easily demonstrated with light. A concave mirror is put into a smoke box which has holes to let in two beams of light. The candle produces smoke to make the beams visible. The beams projected onto the mirror parallel to each other are reflected and meet in front of it. Infrared rays can be focused in the same way. And this has practical application in the solar furnace. A mirror focuses the rays of the sun at a point in front of it. The heat from the infrared rays is concentrated at this point and will soon boil a flask of water. In hot countries, solar furnaces can be used for cooking. Much larger furnaces are used in industry to test heat-resistant materials and to produce power for the machinery. Mirrors are, in fact, among the best reflectors of radiation. But other surfaces reflect to varying degrees. They also absorb radiation. Bright, shiny surfaces reflect more radiation than they absorb. And dark, matte surfaces absorb more than they reflect. The same applies with infrared rays. This is shown by a simple experiment. Both these flasks contain air, and the level of the liquid in the U-tubes will alter when the flasks are heated by the source of heat. After a few minutes, the liquid in the U-tubes has moved, and that in the U-tube of the black flask has moved more than that of the white flask. This is because the dark surface absorbs the heat more rapidly than the light one. This fact is used in the design of petrol storage tanks, which are brightly polished to reduce their heat absorption. Some buildings have light aluminium roofs for the same reason. Different surfaces not only absorb heat differently, they also radiate differently. These two teapots will show this. Both contain the same quantity of water at the same temperature. The detector, placed near the teapots, will give an indication of the heat radiated by each one. The black pot gives a higher reading than the white one. It is a better radiator. This is confirmed later by the fact that the water in the black pot cools faster than that in the white pot. Another way to compare the radiating properties of different surfaces is to use a Leslie's cube. This is hollow, and each of its vertical walls has a different surface, one shiny, one rough, one light, and one dark. The cube is filled with hot water, and the heat radiated by each surface is measured with a detector. The dark surface gives a high reading. So does the rough surface. Both are good radiators. But the light surface gives a low reading. And the shiny surface gives a low reading. Both these are poor radiators. So we can summarize that dark, rough surfaces are poor reflectors, but good absorbers and good radiators, whereas light and shiny surfaces are good reflectors, but poor absorbers and poor radiators. This fact is used in the design of the vacuum flask, which has silvered surfaces to reduce the amount of heat lost by radiation. In addition, the vacuum between the double walls of the flask reduces heat loss by conduction or convection, since both require the presence of a material medium. So the liquid inside the flask is very well insulated, and the flask can be used either to keep hot things hot or cold things cold. Nevertheless, all objects emit, absorb, and reflect radiated heat to some extent. The fire here radiates a considerable amount of heat to the room. The child absorbs the radiation and becomes warm. The furniture also absorbs the radiation, and so do the walls. In fact, all the objects in the room. But these objects don't go on getting hotter indefinitely, because at the same time, they all re-radiate some of the energy they have absorbed. Their temperature rises until a point is reached when they re-radiate the energy as fast as they absorb it. The two processes balance. They then remain at that temperature until the fire is switched off. When that happens, they radiate their energy faster than they absorb new energy, so they cool. This happens with the Earth. During the day, the Earth absorbs the sun's radiation and becomes warm. At night, it re-radiates its stored energy to the atmosphere and becomes cool. But if there is cloud overhead, some of the Earth's radiation is absorbed and some is re-radiated back to the Earth. So clouds act as a blanket at night and help to keep the Earth warm. The spread of the sun's radiation over the Earth's surface determines the climate. Because of the curvature of the Earth, a beam of sunlight at the poles is spread over a large area. At the equator, a similar beam is concentrated on a much smaller area. So at the poles, there is always ice and snow, and at the equator, conditions are tropical. A warm body transfers some of its energy as invisible infrared rays. This is a form of electromagnetic radiation, as are light rays, radio waves, X-rays, and ultraviolet rays. The different properties of these various rays are due to their different wavelength. Infrared rays have a wavelength slightly longer than visible red rays. Like light rays, they are reflected, absorbed, and radiated by different surfaces. Dark and rough surfaces are poor reflectors, but good absorbers and radiators. Light and shiny surfaces are good reflectors, but poor absorbers and radiators.